Moving into the Speos interface, we've established our 3D digital twin, including the road, vehicle, and pedestrian. This allows us to validate the projector's performance within its real-world physical context. I'll start by selecting the road surface. We define its specific material properties like reflectance and texture to ensure the stop logo interacts correctly with the asphalt surface during the simulation. Next, we inspect the projector assembly. We've modeled the internal housing and the LED PCB. By defining these as physical objects, we can account for thermal constraints and internal light reflection that might affect the beam. The core of the system is the gobo stencil. Notice how we can instantly toggle between red and yellow coatings. This allows us to evaluate which color provides the highest contrast and quickest recognition for pedestrians at night. By analyzing these specific spectral properties against the asphalt's reflectance, we ensure maximum visibility in low-light urban environments. Integration is seamless through the optical design exchange. We pull the precision lens array directly from Ansys Zemax OpticStudio, ensuring the light shaping performance matches our mathematical optimization perfectly. By importing the original design file at this stage, we maintain the exact optical prescription. These lenses are assigned specific shot glass properties, providing a high-fidelity foundation for how the light will be steered onto the crosswalk. This seamless data transfer ensures that the mathematical optimization from Zemax is preserved perfectly within our 3D mechanical environment. We also simulate environmental variables using HDR maps. Here we toggle from a bright, sunny afternoon to a clear night. This is vital to ensure the safety logo remains visible even when competing with street lights, moonlight, or high-glare daytime conditions. By testing across these lighting extremes, we validate that the projection maintains the required contrast ratios for pedestrian recognition at any hour of the day. Now we enable the irradiance sensor. This heat map identifies the exact distribution of light power falling on the zebra crossing. It confirms that the stop logo is projected with uniform intensity across the entire 225 mm target area. Finally, we verify our observer sensors and light sources in the simulation tree. With the geometry, materials, and environment fully defined, our model is now ready for a high-fidelity compute run. Let's move to the simulation phase. Before we hit compute, we place our sensors. We have an irradiance sensor on the road to measure raw light power and a radiance sensor representing the human eye. We position an observer at a height of 1.7 meters to simulate the perspective of a pedestrian. This allows us to move beyond just numbers and actually see the results through a human lens. We evaluate if the projected logo is within the pedestrian's natural line of sight while ensuring no light bleed distracts oncoming traffic. By fine-tuning sensor locations, we capture a comprehensive map of both technical performance and user experience. Now we launch the simulation. We are using a direct Monte Carlo algorithm. The software is currently tracing millions of rays as they exit the LED, pass through the lens array, hit the gobo, and reflect off the textured road surface. This high-fidelity compute ensures that every photon is accounted for, including those that might scatter or cause unwanted glare. The algorithm accurately models the scattering effects of the asphalt to predict real-world contrast. This gives us the confidence to proceed without the immediate need for multiple physical prototypes. The simulation is complete and the results are in. Looking at the spectral map, the stop logo is clearly defined. We can see the chromaticity and the luminance values. By checking the heat map, we can verify if the brightness meets local safety regulations. The projection is sharp with minimal distortion at the edges of the 225 mm image area. We can also analyze the uniformity of the light across the entire logo to ensure there are no dark spots. This spectral data is essential for verifying that the color remains consistent and recognizable from a distance. It provides a definitive proof of concept backed by rigorous physical data. Now let's apply the human vision filter. This is a game changer. It adjusts the result based on how the human eye adapts to darkness. Even if a logo is mathematically bright, if it's surrounded by shadows, the eye perceives it differently. Speos shows us that the red and yellow logo pops significantly against the dark asphalt, ensuring a high probability of detection for the pedestrian. This step moves us from raw data to an actual representation of the human experience on the street. It ensures the design is not just technically sound, but practically effective for public safety. To double-check our work, we enable 3D ray tracing. Watch the paths as they move through the glass elements. This visual confirmation allows us to spot any stray light or internal leakage that could reduce the efficiency of the projector. Everything is converging exactly as planned on the crosswalk. Visualizing these paths helps us identify opportunities to further optimize the housing for better thermal or optical performance. It provides a final intuitive verification that our system is ready for real-world deployment. In conclusion, by using this integrated Ansys optics workflow, we've successfully designed, tested, and validated a critical safety system in a 100% virtual environment. We've optimized the lenses, selected the best colors, and guaranteed visibility, all before a single physical prototype was manufactured. Thank you for joining this demonstration.